All right, and also, let me see if I can log into my, okay, yeah, I can see it. Okay, great. I think that's it.
Mm-hmm.
Okay, cool. So I guess I'm ready to go.
Yeah, cool. Yeah, it's recording. You can just do that via TeamViewer.
Do what via TeamViewer?
The whole presentation.
Okay. So we're going right now?
Mm-hmm.
Okay, cool. Okay, so I put together these slides just because it helps me. But the whole point of doing all this stuff, and I suppose the primary goal of this is to kind of to teach you how the Panini projection works, so we can implement it for this game as well as for like Quake or whatever we want to do in the future, and to kind of build a foundation for like what we're doing here. So I actually pulled this from Google Street View, and if I wanted to find a picture that had people in it because that's the best way to kind of see the distortion effects of the perspective projection. And the perspective projection goes by many names. It's like the standard one we use in all games. It's like mnemonic and world map projections. But it's this one, and it's used everywhere.
Is this the rectilinear projection?
Yeah, that's like another name for it.
Yeah.
So, I mean, it's used anywhere where we are trying to project 3D images, right? So this is one instance of it. And you can see that it kind of works in this tunnel vision area of about 90 by 90 degrees. But sort of outside of it, when you try to sort of incorporate the peripheral vision, you get like really bad distortion around like 160 degrees. It's just really bad. So the reason why is because these things are intended to be viewed at a certain focal point, and that focal point is really close to the screen. So you have to actually be right up against the screen such that it incorporates 160 degrees of your actual vision if you are rendering that image at 160 degrees. So you can imagine if you're standing way back from it, like the perspective of this image here, you're kind of like sitting in the back row of this theater. The amount of degrees that image is covering in your field of vision is about, I don't know, like 60, maybe 50, right?
Mm-hmm.
So that's why like a lot of games where you're sitting back on your couch are rendered at about 70 degrees, I think. Yeah. And computer games are kind of rendered at 90. And so yeah, this is kind of the intended focal point of this image and why we get such terrible distortion when we try to like stretch it out. And like all perspective projections, it's kind of intended to be viewed from a single focal point, and I think that's the weakness of this type of projection. And this is like street graffiti, same deal. Cool. So if we want, the whole conclusion to this is like if we want wide angle views on low angle screens, and low angle screens is kind of the medium that we're trying to target here, and perspective projections are pretty bad for that. So instead of using that, we can use Panini, and this is a different photo, but it's of the same place, and you can get much better photos and much higher fidelity if we just use like a better projection that's kind of designed for things like this, which is Panini. Cool. Okay, so that's kind of the concept behind it. Let's talk about how to construct these perspectives. I'm not getting too deep into the math, but I think an overall coverage of these concepts to kind of lay the foundation where we can derive the math ourselves, I think is much better than kind of diving into the math itself. So traditionally when you're kind of rendering things on a screen, you're used to the origin being up here and X positive being that way and Y positive being that way. But projections are made much easier if you just kind of like center the coordinate system. And the reason why is because when you're in 3D space, you're kind of taking the origin to be at the center of the screen and, actually further back from the screen. And Z is kind of into the screen. Yeah, so this is essentially the setup for the screen before you're going to render this 3D space. So once you want to start rendering that 3D space, you kind of pick any point in the space, and then you draw a ray from where you are, which is the origin of the system that you chose, somewhere behind the screen. and you kind of draw a ray to that point in space, and wherever that ray hits the screen, that's how you essentially you convert a 3D point to a 2D point on your screen. So are you familiar with all this already?
A bit, yeah.
Cool. So the idea here is once you have that point, you only really need to look at one axis at a time. So this is the point in space, and you draw that line to the origin, and then wherever that line intersects, just by looking at the y-axis here, is sort of the final y-coordinate of that point on the screen. And it's pretty straightforward. You can kind of just say, you look at this triangle here, and then look at this triangle here, and notice that they're just scaled down versions of each other. So you essentially just divide this by z, and divide this number by the distance to the screen, and then you have a simple ratio that you can use to solve for this coordinate. And you do the same for both of these things. So it's all about setting up the triangles and solving the proportions. It's very simple math. And incidentally, the distance to the screen, it actually controls the field of view. So if this was actually closer to the screen, the closer it got, the wider the field of view would be. Right? Okay. So once you kind of plot all these points using that method that I showed, all you need to do is just connect those lines, connect those dots with the lines, because lines are preserved in perspective projections. All you really need to do is plot the points, map them to the 2D space, and then connect the lines. There's like no real trick to doing that. And incidentally, this is what GPUs do best, is they just draw triangles. And because these 3D triangles map directly to 2D triangles, there's no like warping at all. It's just straight lines. That's what it does best. So if we want to do something like alternate projections, like what Panini is and Mercator and all that other stuff, we have to draw the triangles first straight, which is what the GPU is doing. But then we have to warp the resulting images with something called fragment shaders. And what that is it maps one pixel to another. But we can't just render one, or like rather, if we wanted to render, cover the space around us, we have to sort of render multiple views at once. And in this picture, we're just rendering 3 to kind of cover just partial space. And like once we do that, then we can kind of combine these with the shaders to produce like this output screen. And that's essentially what we're trying to do here, is we're trying to combine all those rendered images into a single one. Because this is the limitation of the GPU. We have to render like these straight triangle type things.
So go back to the perspective. We first project like the person who's standing here, project onto these 3 screens, and after that we project from those screens to this screen with the person being here. Is that right?
The person won't. The person is just here to show that this is the screen that they're looking at, but we're not sort of reprojecting with that vantage point in mind. It's because this is not a perspective projection, so it doesn't make sense to have a focal point in this final output, because there is none, because this is not what people see. It's just like a warping of what the person saw up here. So the only perspectives are only rendered up here, and like it's just something weird down here, right? This is like transhuman now, right?
Okay.
Yeah, tell me if I'm going too fast. Did all the stuff make sense?
It's fine.
Okay, cool.
Makes sense so far.
Cool. Okay, so this last one I showed, it's just kind of haphazard. This is kind of at a weird angle. This is just straightforward. I'm not actually covering anything behind me or above or below. So I kind of want to talk about how we're combining these views. And so The most common one, I just want to look at the left one here, is like is something called a cube map, where you just kind of render 90 by 90 degree views in the shape of a cube, and that's just one way to do it. So you can kind of render 6 views and kind of get that coverage that way. But what I found in Blinky is that we are not restricted to the cube, and if we want to help with performance and kind of only render a certain number of views for like this to like compromise on quality, then we can kind of limit the number of screens. For example, this is just rendering 3 screens. Granted, like these are at a wider field of view, right? So they're about 120 degrees. You can do that and you would cover the same amount of area, right? So this is a triangular prism viewed from above. This is like a cube viewed from above. And the idea with these colors is that they're getting the same image. It just appears differently to each of these screens. Does that much make sense so far?
Yeah, it makes sense.
Cool.
So you get probably some muddiness in the textures, but you render less, right?
Yeah. And you can kind of push this to the limit and start playing with like different overlapping plates. But the idea is like we can do that. It doesn't really matter how we capture the pixels. We just need them, right? So the idea here is like this is the abstract globe that we need, and it doesn't really matter how we get them, and we can kind of play with this to see what kind of performance we can get out of it and quality.
Yeah.
Yeah.
You could theoretically just get the globe if you do ray tracing, right?
Exactly. And that's what Jai has been doing. He's actually rewriting.
Yeah, he showed me that.
It's amazing.
Mm.
Okay. This is like the last 2 slides here, because it's pretty straightforward from here. But so once we have our abstract globe, we need a way to kind of map it to this projected image that we want. And there's 2 ways to do that. And we're getting into cartography now. This is where we can use the hundreds of years of research and practice that these guys have been using, Mercator, and more recently Panini. It's like 10 years old at this point. And I think stereographic was used to kind of map the stars in a way. So anyway, one way to
Panini.
Go ahead.
Panini wasn't used for maps, wasn't it? Used in art, like when painting buildings and stuff like that from the inside.
Right. That's what the creator of it was trying to do, was trying to recreate what he might have used as his projection to paint these architectures. But he never like mathematically documented it, so that's like our way to recreate what he did.
Okay.
Yeah. So there's 2 mappings. Anytime you look up a projection, be it fisheye, Mercator, whatever it is, you're always going to find 2 mappings. And the forward one is the one that takes a pixel on the globe. And this is usually defined in it's usually defined as latitude, longitude. So given a latitude, longitude point on this globe, it will give you an XY coordinate on the projected image. So that's what forward will give you. There is no standard size for this projected image, so it's going to vary from projection to projection. More about that later. That's like pretty important. But once you have this image, to get back to the globe, you have an inverse projection. This is pretty hard to get sometimes because it's not, what's the word for it? It's not analytically solvable to like provide the reverse mapping. That's why whenever you used Winkle Triple in Blinky, it didn't have that inverse mapping because it was, I'm not sure if I'm like getting ahead of myself here, but it was a lot slower to render that one. Notice it was like rendering the front face, the left face, the right face, like stepwise, right? Because it was using the forward map to take each face of that cube and map it to the screen instead of mapping the screen and finding the associated pixel on the globe. So that's kind of...
I mean, what do you need the inverse projection for? I mean, don't you have the globe and you want to know which pixel on the screen to render it on?
That's a good question. So if you have like a pixel on the globe and you want to map it to a pixel on the screen, you would have a lot of pixels that maybe overlap, and you may have gaps between those pixels on the globe. So you would essentially have a point cloud on the screen. So in order to like interpolate those between those that point the points on that point cloud on your screen, you need an inverse projection. So it would say the exact pixel for each pixel on the screen. You don't really care about the pixels on the globe. For every pixel,
there are more points on the globe than points on the screen, and that's why the inverse projection is faster.
Yeah, you could say that. Yeah, but it also lets you interpolate between those points. I don't have any graphics to like help me explain this, but it's very one-to-one. For every image I have for every pixel I have on my screen, like what is the color of that? And it would just look up the abstract globe and like give you the exact pixel that you need. So it's very one-to-one, and it's nice because the screen is all we care about. So this is really good.
And so how do you get the inverse projection?
These are usually provided for you.
Okay.
But there's like a lot of math to solve for it. Yeah, it's just math. We can look at projection code later, and we can even like derive the Panini projection. It's pretty simple, if you wanted to. But like a couple slides more. Okay. So the utility of each of these is different, but I use both of them. So we'll look at the code in the shader later, but the main thing here is that it allows you to scale the image in order to fit the desired FOV. Okay, so if you have a horizontal FOV of 180 degrees, the edge of that image is going to be like right here where I'm clicking, like on the left side and on the right side. So, and I remember I said that the projected image varies from projection to projection. It's going to vary because there's no standard size. They're kind of dealing in their own coordinate spaces. So you essentially have this image, and you have no idea how to resize it to fit the screen in order to cover the field of view that you want. So the idea is that you use this forward projection to map out a point, this point that represents your field of view, which is at latitude like negative 90 degrees. I'm sorry, I said that wrong. Latitude 0 degrees and longitude negative 90 degrees, or positive 90 degrees, it doesn't really matter. And that will give you a point on this projected image. And you can use that point to say, scale it such that this point is at the edge of the screen. And that's how you do scaling.
Okay. So you first project the globe into a texture, and then you stretch it over the screen.
I mean, doing a lot of that work would be kind of redundant. All you're using is you're using this function that you give it two numbers, and it gives you two numbers in return. And one of those numbers represents the width that you need to set the image to.
Okay.
So you're not having to do anything other than use this nice mathematical function, and then it gives you a scale that you can use to stretch your image to fit the screen, to fit your field of view.
Why is the width of the resulting image not always just the width of the screen, or like the window that you're drawing in?
This is probably something I didn't clarify, but we're dealing in the coordinate system kind of set by the projection, and this projection, we're kind of like in this abstract space of coordinates. We're up here, we're in latitude, longitude. That's kind of straightforward. But down here, we're kind of in this abstract XY space, and the image size is. Go ahead.
I'm sorry, isn't when you're drawing anything to a screen, aren't the screen space coordinates always 0 to 1? And couldn't you normalize this space that you get on the virtual map, let's say, like the cartography map, to 0 to 1, and then you would already have screen space coordinates?
I'm not sure how to answer this one. I think, yes, you do have normalized 0, 1 space coordinates, right? But this might best be explained by looking at the shader. But
Okay.
The point is, like, you give this a latitude, longitude, and it gives you a point on the image. That image is, I don't know, like 3,000 something, and then 0 because it's still on the horizontal axis. So the idea is like that number can be anything. So you essentially have to take that number and use it to scale down the resulting image to fit the 0, 1 range, right? So the output is these normalized coordinates, but we have to normalize it in order to like give it to the GPU, right?
Okay, so that's exactly what you're doing. You're just getting the minimum and maximum value so that you can normalize the rest.
Yes, that's the perfect way to say that. It's just the min-max values and then normalizing on that.
I see. Okay.
That was, yeah.
Makes sense.
That's a lot simpler. Okay. Yeah, so that's what it's good for. But like I said, this is not. It's not good to map the point cloud up here to this. This is just used for scaling. Once we have the scale down, it's a really simple matter of mapping every point on the screen to a point on the globe. And it's amazing. This is magical. It's like a bunch of, I don't understand how fast this is, because the GPU is able to do this for every single pixel. I don't know how fast it is, but it's so fluid, and it's all done in parallel for like each pixel some way. I remember struggling with this on Blinky. Like I had to pause if it was taking too long so it could resume the next frame, just so you wouldn't be sitting there for 10 seconds without anything on the screen. So it's like this slow buildup, but now it's just like instantaneous. It's crazy. So this is like the magic of shaders, is that you can do all this stuff in parallel at no cost. So that's what it's good for.
Blinky wasn't using shaders?
It was not using shaders. Like, that's why it was so slow. It's a software renderer. Like, it's all just plain C code, right? Yeah, that's why it was slow. Cool. That is it. We can jump into the code now, but that's all I had for the high level concepts.
Yeah, it's cool.
Cool. All that clear. Cool. How do I get out of here?
Just press escape.
I'm doing that.
Then press F11.
Oh, okay. Thank you for your Windows knowledge. Cool.
You had a link with projections. If we can go over that together. Let me find it real quick. I have it here somewhere. Yeah, I think you already.
Yeah, so one of the things I did with Blinky was just kind of amass all these projections and play with which ones worked and which ones didn't. So if you just open up a random one, you kind of have some parameters here. Some of them are constants used by the forward and inverse mappings. Other ones are kind of settings for to do this initial sizing as a default, and like what to do whenever it's first loaded. But I mean, luckily I don't have to remember how any of this works. I can just pull in these functions, and that's essentially what I've been doing. So if we look at the shader code, you'll notice that there's a lot of like Panini underscore forward, Panini underscore inverse, and these are taken like verbatim from these. I mean, granted, it's a different language. I just had to convert little things here and there. If you look at Panini, yeah, just an inverse and a forward, like we expected. So yeah, let's look at the let's see, Blinky. Is that what you want to do now? You want to look at the shaders?
Yes.
Cool. There's like this thing that takes my hotkeys away. Let me exit. I'm looking for my tree view. Oh, there it is. Okay. Why isn't it showing up? There we go. Okay, so I like to build a lot of small functions because there's so many coordinate systems I have to think of. So anytime I'm switching to a coordinate system, I just create a different function for that. And you'll notice a lot of naming conventions like lat lon to ray. That'll convert a latitude longitude to a normalized ray. What else? This is all the projection functions. Okay, so I have array and I want a color, so that will map to the abstract globe and find the right color. Let's see. Texture to ray. So texture is this is the 0, 1 that you were talking about. It starts out with 0, 1 at the bottom left, and positive in both directions, and I have to convert that to something I'm calling a lens coordinate system. And this is just 0, 0, 0, 0 in the middle, and then 1 on the right, and then whatever the top one is, it could vary based on the aspect ratio. So it's like 1 divided by the aspect ratio. And that's lens coordinates. And then I give those lens coordinates to each of these projections up here, like a stereographic ray. It takes this lens coordinate, and yeah, let's just use this one as an example. So given this lens coordinate, it will use the forward projection, like I said, to find the scale, and it does this by taking the field of view, which is, if it was 180, it would just be 90. And then pull the x-coordinate from that. And the x-coordinate is a scale, and then it just multiplies the lens coordinate, since the very far right pixel is like a 1, and then it applies the inverse to that, and that's it. So at the very bottom, we can kind of look at okay, so given a texture coordinate, which is ranging from 0, 1, 0, 1, we convert it to a lens coordinate, which is like a normalized thing, like I was saying. Mm-hmm. And then depending on the field of view, it will choose the right projection based on what we think is the best projection for that range. And you'll notice at some places, first of all, is that much clearer? Because it's just taking a field of view and it's getting a ray based on the coordinate that we're on.
What are you doing with that ray?
So the ray is the thing we're going to be using as input to get the pixel from the globe.
Okay. So I see. So depending on the projection, you're shooting a different ray. You're shooting the ray in a different direction from the texture to the globe.
Exactly.
But the thing is that the texture and the globe, are they in Euclidean space next to each other? Can you visualize it like that? Is that correct, or?
Are they in the same space? What do you mean by that?
Like, can I imagine an actual ray in a Euclidean space going from a plane to a globe? Would there be a correct representation of what's happening here?
Oh, no. I would imagine these entities as being separate. So the plane that we're projecting on the screen is going to be associated with something on the globe, right? That's granted. But I wouldn't try to imagine the ray going from the screen to the globe. Rather, what this ray represents is the direction once you're at the center of the globe, of like which direction you should face in order to get the color of pixel that pixel needs. Let me go back to the presentation.
Yeah, so you're in the middle of the globe, like the texture is in the middle of the globe and looking outwards.
Mm-hmm.
Like that?
Yeah, so how would you request a pixel from this globe, right? Because you don't know how it was captured. It could have been a cube, it could have been like a triangle around it. The idea is like you need some way to refer to a pixel on this abstract globe, and we use that. I said latitude, longitude earlier because that's what a lot of map projections used. But here I'm using array, which is essentially the same thing. It's just a direction. Yeah.
Latitude, longitude is 2-dimensional and array is 3-dimensional.
True. But it's 2-dimensional on the surfaces of a sphere, which is 3-dimensional. So if you think of array as being from the center of the globe to a point represented by latitude, longitude. Yeah.
So that's how I thought that it could be visualized. Like you're in the middle of the sphere, and the texture you could imagine being in the middle of the sphere, and it's just pointing to one point on the globe.
Yeah.
Where it gets the color from. Okay.
That's exactly what it is. So like imagining the ray from this image to the globe, right? That wouldn't make sense.
Mm-hmm.
Right.
Okay, cool.
So yeah, I hope this much is clear because it's just generating a ray based on the projection. So it's really cool because you can start mixing these rays together in order to sort of transition between them. And that's what this nice mix function does.
Is that a lerp? A linear interpolation? Yeah,
you know all about that. It's just a lerp. So so it should be a slurp because it's supposed to like spherically like rotate one ray to the other. But I mean, mixing is actually fine just by the way that we're computing the ray. It just extends it as far as it needs to go. And
you don't need a slurp because the ray is actually 2-dimensional, right? I mean, the result of the ray is, maybe that's the reason, because you're always pointing from the inside, whatever. I think mixing is fine and you don't need a slurp because the rays, while being 3-dimensional vectors, are always going to point to like
the rays
from
are
the
3D.
center of the sphere. They're 2D, basically, yeah.
No, they're 3D, right? They have 3 components.
Yeah, they have 3 components,
right.
But why does it, did you try a slurp?
There is none for GLSL, which is the language we're working in right now. There's only like a mix. You had to like manually implement a slurp, which I didn't want to do.
Okay.
And then this is just a simple ratio you compute to choose how much to mix them.
Why do you subtract like the FOV if you subtract 120 to get much it's over 120?
This
okay, it's in 20-degree steps. I see it. Okay, that's not exactly 20 degrees. Okay, I see.
This code really excited me that it was that easy to do. I was a little worried about transitioning, but that ended up being really straightforward. What am I doing here? Mercator's weird because I couldn't really transition some ray to, or equirectangular is weird because you can get to a point where a pixel actually doesn't map to anything because it's like in the void. It's not an infinite image. It's very well defined. It's like 180 by 360. So you can't really transition a pixel to something that isn't there. So anyway, it's not too important though. So whenever I get to a point on a void, I just have a 0 vector. And that's what, I think that's what this one does. Anyway. We probably should have started at the top. Do you want to work our way out from the main function and see what it does?
Yeah, let's do that.
Okay. So let's find out where the color is. Are you familiar with GLSL at all?
A bit, yes.
Okay. Well, this is an output color. This is used by the shader. I let Jai kind of worry about everything that happens outside the shader. But the idea is you need to map that to whatever the color the pixel is. So that's what this is. It's kind of like this implicit output variable. And texture chord is sent by Jai's code. And this texture coordinate is something that ranges from 0 to 1 for both dimensions.
The vertex, like which vertex is that? Are those the two triangles or the one triangle that is stretching over the whole screen?
Which vertex? This one
Like,
I have here?
you're rendering like 6 cameras, 2 textures, and this is the fragment shader that's being run. Like at the end, you have only 2 triangles covering the whole screen, and the fragment shader is running on those. And so these are the coordinates of screen space. These texture coordinates are screen space coordinates from 0 to 1, right?
That's exactly right. It's just a two triangle primitive that is essentially colored with a shader that is looking at these textures that are being sent here.
Okay.
Ideally, I want these to be sort of more abstract so we can play with the quality instead of assuming a cube, right? Okay, so it's very simple. This is our output and this is our input, and we're going to start messing with it in this text color function. I'll get to this anti-alias soon. This is actually really interesting. Jai did that. But for this text color, what are we doing? So we're taking this texture coordinate and we want array from that. So we go to that textured array function, and this is where we're kind of finding the right ray and mixing all these projections together. So all these functions are just dealing with one thing and sending it to the next. So once we have that, like I said, if the ray is a 0 length array, which is what I use to kind of represent the void, this void space, we just return the background color. Otherwise, what do we do? Okay, we say ray to color. So we try to actually pull from this abstract globe that pixel that we wanted based on that ray. And right now it's hard-coded to kind of look for the right texture to pull from. And it does some math to kind of convert this normalized coordinate from the center of the texture to like the top left, because that's what UV coordinates are in. So this is all hard-coded. We should convert that over later.
Okay, so what's happening exactly in ray to color? I didn't get that. You have the ray from the texture to the globe, and then depending on the coordinates of the ray, you're picking the right texture to look from.
Right. So let's go back to this. So right, in the abstract globe, you have like a vector going out towards this red space. So then we go back to the actual implementation of the globe, because that's the only way we can get it. So you can see that the ray is pointing towards this section. So it's like, okay, you want the texture from this side, and then it's finding the exact coordinate on that texture, and then it's sending you that color. So it's having to do a lot of manual work to find first the input screen that has the color that you want, and then it converts that ray into a pixel on that texture that you can get.
Yeah. Okay.
Yeah. Likewise.
So all of the magic is in picking the right ray, and after you have the ray, it's just you trace the ray and get the color.
Yeah. I mean, there's some magic in picking the color for that ray based on, because there can be like a bunch of different types of what did I call them? Just globes. All these like different like tetrahedron that you can have. Yeah. But that's pretty straightforward math once you know it. So that's exactly what this is. It's doing some magic to find the color associated with that ray. Cool. And Jai did some crazy stuff that I just put into a function here called isRayOnCursor, because that's what I think he's doing. So if you want to draw the cursor, I think it's actually just looking at the ray and somehow figuring out if it's on the cursor, and then what it does is it adds this this color to it, and I think that effectively inverts the color by making it wrap around. So you can see every pixel on the cursor is going to be inverted, so you can see what's there.
That's what you're using for the static mode, right? Where you don't move the camera with your mouse, but you have like the camera is static, but then you can click around. Is that what this is used for?
No, that's there's some. I ripped that code out. This is just a center. No, he did some tricky stuff with drawing a circle. This is just a cross in the center of the screen.
Okay, I see.
Yeah. I can show that. I can just run it. Have you run this stuff yet?
Well, not from the code. I've run it. I've downloaded the mod and run it in Minecraft, but
okay.
I haven't compiled the code or anything like that yet.
Well, you can just run the script if you want, and it will. Actually, do you have like Git Bash or something?
I'm not a fan of Git, but I think I'll have to get it for this project.
It's a little weird because you have to. Let me show you. This is like an important detail. Now we're getting into the Java code. Okay. So there's a class for every type of projection that you can use, or rendering mode is what he calls it. And at the top of every one, you have to have like a fragment shader variable. And this is the string that is contained in this file. So we actually have to run this update script in order to copy all this stuff into the string. So that's all that the play script is doing.
I showed him how to load text files out of a jar file. So maybe you won't need to do that anymore, and you can just
That'd be great.
keep it in the shader file.
That'd be awesome. I just wanted to show you the inverted crosshair. Oops. Okay. I have the Rubik's Cube on, which I should turn off. But you can see at the center of the screen, it's just inverting all the colors.
Yeah, I see it, yeah. Okay,
Yeah.
So that's that.
Yep.
And so instead of doing that in a post-processing step in a second shader, he just does it right there. Yeah, that makes sense.
Yeah, I don't know how to combine shaders or if that would make sense, but yeah, that's outside my knowledge.
Well, you would need to have a second small rectangle geometry in the middle of the screen, and then run this invert shader only for that. And it's a bit unnecessary. So he combined it in this shader. I see.
Yeah.
Okay.
Cool. I think that's about it. Okay. Anti-alias. This is kind of cool. He is taking 4 samples. He told me he actually took 16 samples, and it didn't affect the speed at all. But it's interesting. So for every texture coordinate, or for every offset that we have, and he's actually dumping this from. He's sending all the offsets over into the shader. So they're already there in this array.
Makes sense.
Yeah, it's just adding it to the texture coordinate, and once it gets the color for that offset, it adds it to this 0 vector, and then it just sums it, averages it all together to get like this average color. So that's a really cool way to get anti-aliasing for real cheap.
Yeah, this is just standard multi-sampling anti-aliasing.
Oh, is that right? Cool.
I think that's it, yeah.
Cool.
Which is, the best kind of anti-aliasing.
Oh, yeah? Cool.
Yeah, it's the highest quality. I mean, I think there's a couple of different modes how you average the colors then together. If you do 16 times, then maybe just getting the average of all 16 is not the best, but you get intermediate averages and stuff like that. And I if I remember correctly, maybe the quality is a bit better, but with 4 times more, 4 samples, it's this is the way to do it, and yeah.
Okay, cool. I'm just surprised at how fast it was because I was trying to get some performance back, and it didn't seem to affect it, the anti-aliasing. But it's Minecraft,
Awesome.
and there's huge pixels everywhere, so it doesn't really matter, I guess.
Yeah, maybe.
Um,
But fragment shaders don't really care. Don't really care how the textures look. You have the same amount of calculations per frame anyway, so it doesn't matter that the graphics are blocky.
Right. Cool. Yeah, most of this code is just projections that I ripped from the scripts, where I pulled from a lot of different sources. But yeah, you're asking, I guess, primarily to figure out how to implement Panini. Did you want to derive it, or is this code fine? Did that satisfy?
It would be like, how complicated is deriving it?
This looks complicated. This is more of a general version. I think I had a much easier version, but I just took the general one in case we wanted to tweak this D parameter or whatever, which I don't think I ever will. I don't know. Maybe we can derive another time then.
What does the D parameter do?
You can pull like the Panini paper, and I think it, I have no idea what it does. Is there a paper here? I thought I remember one. Like PDF or something. There it is. So you can find it in this paper. He has like a general projection which does some extra warping to get some favorable characteristics, but I think it depends on the image. He looks at the image and he tries to straighten it out a little more, and then that might be what the D parameter is for.
Give me a second to copy that URL. Give me the cursor. Thanks.
Yep. I think somebody used this in a game before. I remember seeing a video of it, but he did it in post-process. So he just rendered Unreal or whatever, and a really high FOV.
Was it Panquake?
No, that was Wouter's mod. He did that. Panquake was just it was really cool. He just rendered vertical slices and turned left and right, so he would render like a vertical slice. So yeah, thank you. He would render the screen at this vertical slice, then he would turn the camera and render it this way, and he did it so many times. And like I was so surprised because he told me like it didn't affect the speed at all. Like it could just, because we were rendering six views, right? Originally, or he was in Fisheye Quake, and then if you just only render a sliver of it, I don't know, it was like really fast. Anyway, so this is
look here, you can here you can see the artifacts for the slivers, I think. It's a bit like a rolling shutter.
Oh, you're right. Actually, it may not be like a sliver. It looks like it's about that size, maybe? I don't know. It looks pretty smooth, like these.
Yeah.
I don't know. But anyway, we don't need to resort to that anymore because we have shaders and we can just use like an inverse mapping.
What Panquake, do you know how rolling shutter works?
I think so. It's like
yeah. So what Panquake did is basically having a camera with a rolling shutter and spinning it quickly.
Yeah, like I think they call that cylindrical like, I don't know, projections or whatever. Like when they would take a big picture of our entire class, they would put us on bleachers and then do this sweeping image across the bleachers. Yeah.
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 What are bleachers?
Just like road seating and stadiums.
Oh, okay.
Yeah. I guess that's what we call them here.
Mm-hmm.
Cool. Did you get everything you wanted out of this?
Yeah, I guess so.